Hi, thanks for joining me. Today we're going to be covering Article 500 of the National Electrical Code, which covers hazardous locations. This is going to be based on the 2017 edition of the NEC. A little bit about myself. My name's Ryan Jackson. I've been in the industry since 1996, so I guess that's about 23 years now. Most of that time was as an inspector. I was an inspector from 2001 through 2018, I believe, and I've also been an instructor since about 2003. So my main job is I teach seminars, I write textbooks about the NEC, I do expert witness testimony, things of that nature. If you want to get in touch with me, please don't hesitate to do so. My email address and phone number are right there, and please don't think that you're wasting my time if you get in touch with me. I take great pride in being available to help people out with their code-related questions. So please feel free to get in touch with me if you think I can help you. So when it comes to hazardous locations, this is a tough subject, and for a lot of people it's either your whole world or it's something that you're never going to deal with. So I'm going to try to cater to both of those. So if hazardous locations are your whole world, maybe some of this stuff is going to be a little bit basic for you, and I apologize, but maybe it's a refresher. If hazardous locations are new to you, then I think you're probably going to be inundated with a lot of information, and you might have to watch the video twice. But either way, I think you're going to get something out of this class. So when it comes to hazardous locations, that's an area where a fire or explosion hazard exists due to flammable gases, or flammable liquid produced vapors, or combustible liquid produced vapors, or from combustible dusts, or what the code calls easily ignitable fibers and flyings. All of these create a more dangerous situation than we have in, say, a house or even a typical commercial building, so the code has special requirements for them. In order to protect us against fire, we need to understand the properties of fire and what creates a fire or an explosion. So for combustion, we need a flammable or a combustible liquid or vapor or a combustible dust has to be present, and that has to be mixed with oxygen or an oxidizing compound in order to create an ignitable mixture. So we need to have the fuel, and we also need to have oxygen or an oxidizer, and that creates a flammable mixture. Once we have that flammable mixture, we apply a source of energy to it, and for this discussion we're going to limit that source of energy to heat. So we'll apply heat to that mixture, and that will create the reaction that we call fire. This is often described in the context of the fire triangle, and this is a concept that's been around for decades, probably longer than that even, but it's quite valuable and it's accurate. So I have to have three things to have a fire. Number one is the fuel source. If I don't have fuel, then obviously I can't have combustion. So for the purposes of this discussion, the fuel is going to be either a flammable or combustible gas or vapor, and we're going to talk about those, or a combustible dust, or an easily ignitable fiber or flying. So those are the types of fuel sources that we're going to talk about, because those are the types of fuel that the code addresses. We also need to have oxygen or another oxidizing substance, and then we're going to apply heat to it. And the heat that we're going to be talking about in this discussion is going to be limited to arcs and sparks, or heat from luminaires and similar equipment. Have you ever been in your bedroom at night and you walk over and you turn on your light switch and you see a little blue arc inside the switch box? You can see it through the faceplate. It's kind of cool if you're an electrician and you know what that is, because what you're looking at is a series arc. The contacts inside the switch are a make and break contact. You turn the switch on, you close the contacts, and it creates a little tiny arc. It's cool when that happens in your bedroom. When that happens in an area that's full of gasoline vapors, it's really not that cool. So that's what we're trying to address. The arcs and sparks that are created from electrical equipment. And mainly, those are found with what we call make and break contacts. So contacts that make and break, like a switch. Or from heat from luminaires or similar equipment. I'm sure we've all changed a lamp in one of our lights that was on and was too hot, and you burn your fingers, right? Well, obviously that is heat, and that can create a fire if we have the right amount of fuel and oxygen. So we need those three components: fuel, oxygen, and heat from electrical equipment, either an arcing, sparking type of heat or surface heat on a luminaire, a light fixture, or a motor or similar equipment, maybe a transformer. The thing about the fire triangle is that if you remove any one of those three components, then the triangle collapses and we do not have the properties that are needed for combustion. So if I remove the heat, then I can't have a fire, right? If all I have is the fuel and oxygen but no heat source, then we're obviously not going to have ignition. If I remove the fuel, again, we're not going to have ignition. Or if I remove the oxygen. The code provides ways to remove any of those three components and create a safe environment. And that's really what Article 500, and to be more specific, Articles 501 through 516, that's what those articles really tell us how to do, how to remove one of those three facets and remove the risk. Now, there are exceptions. You always need heat and you always need fuel. You don't necessarily always need oxygen to create a fire. I mean, you can have a fire in outer space, which is a vacuum, so how do you have a fire out there? Well, there are elements, chemical compounds, I should say, that are self-oxidizing, that are oxidizers. And one of those is actually nitrocellulose, which is what they used to use for film back in the 1920s and 30s. And in fact, in the National Electrical Code, I believe it's Article 520 that talks about motion picture theaters. There are special rules in Article 520 because of the dangers associated with nitrocellulose film. So nitrocellulose film is an example of a self-oxidizing compound, and believe it or not, if you've never had your hands on nitrocellulose, you actually probably have. Ping pong balls are made of nitrocellulose, and they're remarkably flammable, as you can see in the video here. That's just a regular ping pong ball. It's not doused in gasoline or any other sort of fuel, but it's nitrocellulose, which is incredibly flammable and a self-oxidizing polymer. So there are exceptions to all rules. Generally speaking, you need heat, oxygen, and you need the fuel. Here in this video, of course, if one ping pong ball makes a really cool fire, then obviously 1,000 ping pong balls must be an even better fire. So we'll watch our friends here, and at some point, I'm sure going through their mind is that point that we've all had where it's like, you know, this seemed like a really good idea, but maybe it wasn't such a good idea. What does it look like when we light 1,000 ping pong balls on fire? Some things, of course, are more flammable and that's why we have special requirements for them. 520 exists because of the danger of nitrocellulose. Nitrocellulose is much, much more dangerous than you would ever think it was. So, in fact, I've seen the Quentin Tarantino movie, Glorious Bastards. Remember the end scene with the film. So, there you go. That would be a hazardous substance. We have special rules for that in the NEC because of the obvious risk associated with it. We also have rules for other fuel sources. Again, flammable or combustible liquid produced vapors, and combustible dusts, and easily ignitable fibers and flyings. Now, the ignition sources that we're going to talk about in the code, we're talking about energy or heat from electricity, so switches, circuit breakers, motor starters, push buttons, and other make and break contacts that produce arcs or sparks. Make and break contacts is a phrase that you're probably going to hear me say a lot over the next hour or 2 hours. Make and break contacts is public enemy number one when it comes to a hazardous location, because a make and break contact creates an arc, and that's 1/3 of the fire triangle. The other ignition source that we concern ourselves with the NEC, again, is surface heat. Luminaires, motors, transformers, or other equipment that has enough surface heat to ignite the surrounding environment. So those are the risks that we really have in the code. We need to remove the ignition source, or we need to remove the oxygen, or we need to remove the fuel. If we remove any of those three, then that fire triangle falls apart, and we no longer have the required components for combustion. It's important to remember the scope of the NEC. The NEC only applies to electrical installations. It doesn't apply to usage, and it doesn't apply to work practices. The reason I bring that up is that issues like static electricity, or housekeeping, or dropping tools, and things like that are not addressed in the code, because the code covers what? Electrical installations. It doesn't cover static electricity. That's not an installation issue. It doesn't cover housekeeping, and housekeeping is essential in hazardous locations, especially in Class 2 locations, those locations that are hazardous due to the presence of combustible dust. Dropping tools. If you drop a metal tool on concrete, it can arc, right? And that's not a big deal in 99.9% of our lives. But if you're in an area that's full of gasoline vapors or methyl ethyl ketone or whatever it might be, that can be, well, quite frankly, that can be the end of your life, you know? So I'm not going to say that that's not important. It is important. It's just not covered in the NEC. The NEC covers electrical installations. Let's get into the NEC. Article 500, Hazardous Locations, Class 1, Class 2, and Class 3, Divisions 1 and 2. The scope of the article. 500.1 contains a scope which is a bit odd because it's actually a scope not just for Article 500, but a scope for Articles 500 through 504, which is a little unusual. Articles 500 through 504 cover equipment and wiring in Class 1, Class 2, and Class 3 hazardous classified locations. The NEC uses the term hazardous classified locations. And it does that because we don't want to provide any sort of misconception that there are areas that are not hazardous at all. I mean, look, any area is hazardous, right? Obviously, I mean, walking across the street is a hazard. So, hazardous classified locations. Now, that's a mouthful. I'm not going to keep on saying that phrase over and over, so I'm just going to say hazardous locations. But when I say hazardous locations, obviously I mean hazardous classified locations. There's a lot of informational notes in Article 500, an inordinate amount, really. And I'm not going to cover all of them, but I will cover some. Informational note number 1, the unique characteristics of explosives, pyrotechnics, or blasting agents are not covered by the NEC. So, here we have an Iron Maiden concert. You can see my taste in music. So we're blowing stuff up. We've got pyrotechnics and everything else. Is that a hazardous location? No. No, not at all. If that was a hazardous location, we would blow up. A hazardous location is hazardous because you have fuels around, like gas vapors and combustible dust and things. Think about it. If I had a bunch of gas vapors on the stage and I'm intentionally lighting off fireworks, we'd blow up, right? So the code doesn't get into explosives, pyrotechnics, blasting agents, things like that. That's not what the code covers. Another informational note says that Class 1, Zone 0, Zone 1, and Zone 2 are similar to Class 1 Divisions 1 and 2, and they're discussed in Article 505. The reason that I have a map of Europe here is because the class and zone method of classification is very common in the European Union. We're not going to cover that in today's class, but I will just mention that it does exist, and in the NEC you can actually use the zone method of classification and Article 505, but it would be unusual. And before I forget, if you're into zone classification, there's one rule that is an absolute deal breaker in Article 505, and that is your equipment has to be marked AEX if you're going to use it in an NEC regulated installation. And a lot of zone rated equipment does not have that marking. So we're not going to spend any more time on the zone method. other than to say that it does exist. And you'll notice that there's Zone 0, Zone 1, and Zone 2. We only have Class 1 Division 1 and 2. They have Class 1, Zone 0, Zone 1, and Zone 2. So just letting you know that it does exist. If you're working in a facility, one of the facilities where I teach actually uses the zone method, but it's very, very unusual. The next informational note is quite similar. It says Article 506 covers combustible dust and easily ignitable fibers and flyings that use the zone system once again. So zones 20, 21, and 22. And once again, we're not going to spend any time on the zone method of classification. We're going to stick to class and division. 500.1. Other than the specific areas in Articles 511 through 517, the code does not classify areas. This is critically important. The code does not tell you. I get calls all the time. I'll have somebody call me up and they'll say, "Hey Ryan, I'm wiring a building and they've got methane gas. What class and division is that?" And I don't answer because I can't. The code doesn't classify the area for you. That has to be done by a group of individuals. We'll talk about that here in a minute. Because every industrial facility, every hazardous location is different. Now, there are some areas that we do classify. 511 through 517, that's going to be your commercial garages. Fuel dispensing, gas stations, right? Bulk storage facilities, paint booths, areas like that, aircraft hangars. You know, with gas stations, we've pretty much got it figured out. You know, I mean, seriously, how many gas stations are there? Right? They're all pretty much the same. We know the hazards. It's gasoline. We know the properties of gasoline. We know you've got a dispenser. We're going to classify the area around the dispenser, maybe from the concrete up 18 inches, 20 feet from the dispensers, Class 1 Division 2, inside the dispenser, Class 1 Division 1, underneath the dispenser, XYZ. So, you know, gas stations are all the same. Commercial garages, they're pretty much all the same. Either you're doing engine overhauls or you're not. Either you've got a below grade pit or you don't. You know what I mean? So for those areas that we've done millions of, yeah, the NEC classifies the area. But outside of those, the code does not classify the area. Classification has to be done by people that are familiar with the facility and the dangers of the products involved, like engineers, fire professionals, insurance underwriters, facilities managers, and other qualified persons. I want to be very, very clear on this. I am not going to tell you how to classify an area. I'm not going to. And the reason I'm not going to is because I can't classify your area. In my opinion, no one person should be classifying locations. That's just my opinion. Feel free to disagree with it. But I think you need to have the owner of the facility involved. They need to be honest and they need to be transparent about what they're doing on a day-to-day basis. What do you do Monday through Friday? That room over there, what do you do in it? I see that you've got barrels of gasoline. Are they always closed? Are you just storing gasoline there? Do you open those barrels? Do you transfer liquids inside of that room or not in that room? I need to know what you do. I need to have engineers involved. I need mechanical engineers, not just electrical engineers, because I need to know how much air is in that facility, right? What's the cubic feet of the space? How much ventilation do we have naturally through windows and doors? How much mechanical ventilation do we have? How much mechanical ventilation do we need to dispel all of the vapors and gases that are inside of the area? I might need electrical engineers to understand the electrical equipment that we're using. How hot does it get? Does it have make and break contacts? We might need fire professionals, insurance underwriters. You might need somebody that's quite familiar with chemistry and the different chemicals involved. It's not a one-person operation classifying a location. I'm going to tell you the fundamental concepts that you need to understand for area classification, but I am not arming you with the knowledge required to classify a location. I want to make sure that we're all clear on that. And I'm not giving you that information because I can't. I don't classify areas, and neither should you. It needs to be a group effort of qualified persons. 500.4. I'm going to start getting into the actual rules here. 500.4, in my opinion, is one of the most critical sections in all of Article 500. General requirements A, documentation. I am a stickler on this requirement. Classified areas have to be properly documented, and that documentation must be made available to those that design, inspect, install, maintain, or operate the equipment in the hazardous location. When I was an inspector, this was easy. If you submitted plans for a building that had a hazardous location, I did not issue a permit until the hazardous locations were properly documented. I need to know what class, what division, to what extent, as far as the square footage of the area. From the floor up, how many inches? From the ceiling down, how many inches? Near the door, how far out does it go? What's the group rating of the chemicals? What are the chemicals? What's the auto ignition temperature? I need to know all of that information. If I don't have that information, I can't inspect it. And if I don't have that information, I can't install in that area. So areas have to be properly documented, and we've got to have that documentation available to people. So here in the photograph, we've got area classification drawings. I required that before a permit was issued. At facilities, I think that you deserve and you have to have the classified area documented. This is an example from one of the facilities where I consult. It's blurry, and that's intentional because I don't want to point out anything that might be that might be confidential. So the red areas are Class 1 Division 1, the yellow areas are Class 1 Division 2. So here we have it in the form of a blueprint drawing. They also have a narrative at this facility. You can look at the file in the building, and it will actually tell you in Word format, it will tell you what the classified area is. It will say, okay, yes, this is a Class 1 Division 1. From the floor up, X inches. From the ceiling down, X inches. Within a certain distance of the door, so it will tell you all of that. And you have to have that information or you can't possibly do your job. So I'm a big believer in documentation. Subsection B, reference standards. I know that this is a bit blurry. It's not my intention that you can read all of this. You guys have a copy of the NEC. If you don't, you should. I simply put this up here so that you can see the number of documents that we have here in this informational note. It says, look, helpful information can be found in other industry standards and publications. So NFPA 30, NFPA 33, NFPA 34, NFPA 59, NFPA 499. You get the idea. There's notes and notes and notes of all of these different reference standards that are all valuable and should be consulted based on what you're doing. NFPA 55, compressed gases and cryogenic fluids. If that's your world, then you probably ought to have that document. If that's not your world, then there's no reason to go out and purchase that document. But we do want you to be aware that there are standards for just about anything that you can conceive of. Another note says being familiar with standards by NFPA, API, ISA, and others, as well as having industrial experience may be helpful when classifying areas. Now, I put up here NFPA 497 and 499 because I think those might be the two most commonly used standards when it comes to hazardous locations. 497 is the recommended practice for classifying Class 1 locations, flammable liquids, gases, or vapors, in chemical process areas. And then 499 is the Class 2 version of that for combustible dust. NFPA 30 is another really good document. That's actually the standard for area classification. So NFPA 30, NFPA 497, NFPA 499, I think are very helpful indeed. Some of the other NFPA standards I'm sure are quite helpful as well, but they're very specific. I'm not going to spend any time reading the recommended practice for cryogenic liquids because that's not my world. All right, 500.5, classification of locations. Locations are classified based on the presence of ignitable materials and the likelihood that the quantity is dangerous. All right. Each room or area is classified independently. So here we have a commercial garage, and this is kind of a deja vu moment for me because I was actually at this place yesterday. This is right by my house. We're going to classify each area independently. In the garage itself is probably going to be a class 1 location. We're going to have gasoline vapors and things like that, so it's a classified location. But what about these 3 rooms here in the background? Back here is where I buy parts. In here is the customer waiting area, and in here is an employee area, the cashier's booth. Am I going to classify those 3 rooms? Probably not. We're going to classify areas based on the presence of the ignitable material. Do you really have a lot of gasoline vapor in the customer waiting area? I don't think so. If you did, you're probably not going to have customers, right? I mean, let's be honest. So you're probably not going to classify that area. The code doesn't get into things like, does the door need to be self-closing? Does it need to have a smoke gasket? Does it need to have a door sweep? The code doesn't get into that. That's why we need design professionals to make that determination. So it's based on the presence of ignitable materials and the likelihood that the quantity is actually dangerous. I was talking to a person who was quite sharp, really. He was a mechanical engineer, and he teaches seminars on the mechanical code, on the IMC. And he was talking about how one of these days, he was convinced, one of these days, we're going to hear about a fingernail salon, right? A nail salon. He said, man, you see these things, these nail salons, and they're always in like a strip mall, and right next to the nail salon is a pizza place, and they've got like the big brick oven, pizza oven, and they get super hot, and man, they're right next to the nail salon, and the nail salon's got acetone. One of these days, man, we're going to read about it in the paper where the whole strip mall blew up. And he tells me this, and I'm just like, seriously? Come on. It's fingernail polish remover. Yeah, it's acetone, but it's... Seriously, did you classify your bathroom as a class 1 location? You have fingernail polish there, right? It's not... We classify areas based on whether or not you have ignitable materials and whether the likelihood that the quantity is actually dangerous. A bottle of fingernail polish remover is probably not worth classifying the area over. Now look, I'm not telling you how to classify the area. I'm just telling you, in my world, I'm not going to classify an area based on the presence of a bottle of fingernail polish remover. I'm just not. There's an informational note here that says you should save money and reduce risk by placing as much electrical equipment as possible in an unclassified area. Yeah, I mean, this is not something that the code would normally tell you to do. The code doesn't really tell you about saving money, but it does concern itself with reducing risk. Here in this photograph, on the other side of this wall, this is just a small little building in a parking lot. On the inside of this building, there are barrels and barrels and barrels of gasoline. It is very much a Class 1 Division 1 location. And I know we haven't talked about that yet, but help me out here. So, could I have a panel and a disconnect and a fire alarm? Could I have all that stuff in a Class 1 Division 1 location? Sure. You bet. They make panels that are suitable for use in a Class 1 Division 1 location. You don't buy them at Lowe's and Home Depot. You don't even go to your electrical supply house and say, hey, yeah, I need a Class 1 Division 1 panel board. No, that's not how that works, right? They make them, but boy, you're gonna be smashing your piggy bank if you want to get one of those. So this rule is saying, look, save yourself some money, but much more importantly, save the hazard. Reduce the hazard by putting as much stuff as possible outside of the hazardous location. Put it in an unclassified location. Now, by the way, this is the first chance for me to bring this up. An unclassified location is defined in Article 100, and it is pretty obvious. Any location that's not classified as a class or zone location in Articles 500, 505, or 506. So, here's like an Oktoberfest little beer thing at the ski resort where I teach sometimes. Obviously, that is not a hazardous location. That's an unclassified location. So an unclassified location is an area that's not classified. But this is the first chance to bring up a defined term, so I wanted to do that. And while I'm talking about that, if you're familiar with previous versions of Article 500, we used to define everything in 500.2. We no longer do that. In the 2017 code, they moved all of it to Article 100. So all of these terms, combustible dust, combustible gas detection system, control drawings, dust type, purged and pressurized, non-incentive stuff, all of that was moved to Article 100. So if you're following along in the code book and you're familiar with 500 and you're wondering, well, where did the definitions go? They all went to Article 100. And they all have, parenthetically, CMP 14, which means Code Making Panel 14. That is the group, the Code Making Panel of the NEC that has purview of that particular definition. So in other words, if I submit a proposal to change the definition of combustible dust, my proposal, my public input or public comment would be voted on by Code Making Panel 14. Not really information that most people need to know, but they decided to put it in there nonetheless. All right. 500.5b, Class 1 locations. Here's where we really start taking off here. A Class 1 location is a location where flammable gases, flammable liquid produced vapors, or combustible liquid produced vapors might be present in ignitable mixtures. All right. We just said a lot of different phrases, and we said them fairly quickly. And we're going to have to break these things down and actually understand what a flammable gas or a flammable liquid or a combustible liquid is. Let's start with flammable liquids. This is defined in NFPA 30. A flammable liquid is a liquid that has a flash point below 100 degrees F. And I apologize if you're into Celsius, I'm not. So we're going to go with Fahrenheit. Flammable liquids have a flash point below 100 degrees F. And we're going to talk about what a flash point is here in just a minute. Give me a second. But flammable liquids, less than 100 degree F flash point. Compare that with a combustible liquid. Combustible liquid is a liquid that has a flash point above 100 degrees Fahrenheit. So this is a diesel fuel dispenser. Diesel fuel has a flash point of somewhere in the neighborhood of 125 degrees F. So that is not a flammable liquid. That is a combustible liquid. And there is a big difference between a flammable liquid and a combustible liquid when it comes to area classification. When we start classifying a Class 1 location, we need to know the different characteristics of the chemical compounds that we're dealing with. For the most part, what we need to know is vapor density, flash point, upper and lower flammable limits, and auto ignition temperature. There are some other characteristics that we might need to know as far as the chemicals are concerned, but these are the main ones. We need to know. It's not enough to know that I have, acetone, right? Okay, well, this is hazardous due to the presence of acetone. Okay, well, what makes acetone special? What's the vapor density of acetone? What's the flash point? What's the upper and lower flammable limit or explosive limit? What's the auto ignition temperature? All of these things have to be known. So the vapor density. The vapor density, and this is kind of a tough definition. This is from NFPA 921. It's the ratio of the average molecular weight of a gas or vapor to the average molecular weight of air. Okay, so oxygen is the basis of comparison, or when I say oxygen, the environmental air, I should say, right? So environmental air is 1. It's not 1 gram per centimeter cubed or anything like that. It's just, we just call it 1, okay? Gasoline vapors are 3 to 4, which means gasoline is 3 to 4 times heavier than oxygen, than the atmosphere. Does that make sense? Helium, although helium is inert, so you're not going to light helium on fire. But helium is lighter than air, obviously. So helium is going to be something lower than 1, 0.95 or something like that. So with vapor density, the concept is this. Some gas materials are lighter than air, and some are heavier than air. Lighter than air gases are those with a vapor density of less than 1.0, and they tend to dissipate rapidly. So if I've got a lighter than air gas, that is going to rise, obviously, and it also, thankfully, has a way of just kind of dissipating into the atmosphere very, very quickly. Heavier than air gases are those with a vapor density that are greater than 1.0, and they tend to fall to the low points. Heavier than air gases, unfortunately, they tend to hang around. They accumulate or puddle unless they're dispersed by natural or forced ventilation. Let's look at a couple of common ones. So as I said, oxygen or environmental air is 1.0. Acetone is 2.0. So if I have an area that I'm classifying due to the presence of acetone, I'm going to be much more concerned with the area near the floor than I am with the area by the ceiling, because it's a heavier than air gas. Compare that with acetylene, and that is the opposite. Acetylene has a vapor density or specific gravity of 0.9, meaning that it's lighter than air, and therefore if I'm in an acetylene-enriched environment, I'm going to be more concerned about the ceiling than I am the floor. Likewise with ammonia, that's 0.6. Gasoline is 3 to 4. It's expressed in a range because not all gasolines are created equal. How much ethanol content do you have? What's the octane? You know, there's a lot of variables when it comes to gasoline. So 3 to 4. Methyl ethyl ketone, 2.5. Propane, 1.6, both heavier than air. The next definition is flashpoint. Flashpoint is defined in NFPA 30 and some others. That's the minimum temperature of a liquid at which sufficient vapor is given off to form an ignitable mixture with the air near the surface of the liquid or within the vessel. All right. So in other words, here we have this nice young lady who's pumping gas and enjoying herself a cigarette at the same time. She might learn one of those life lessons that we hear so much about. Does she need to be concerned with the fact that she is smoking while pumping gas? The answer is almost certainly yes, because gasoline has a very low flash point. And let me show you here really quick, and then we'll explain it. Acetone, -4. Acetylene and ammonia don't have a flash point because they're a gas. Only liquids have a flash point. Gasoline, the flash point is somewhere between -36 and -50 degrees F. Let's go back to the photograph. If she's pumping gas and she has an open flame right by the gas, it better be extremely cold where she's pumping that gas. If she's pumping that gas in Alaska in January, she might be okay, right? Because the temperature of the liquid might be less than -50. Let's just be honest. It's not going to be that cold. You know, the air might be that cold, but the gasoline, the liquid, it's in an underground containment. It's not -50. It's going to be warmer than that. So the gasoline is pretty much always being used above its flash point. And as long as the liquid is above its flash point, it is creating vapors that are flammable. Methyl ethyl ketone, MEK, bad stuff. If you're having MEK that is warmer than 16 degrees F, it's giving off flammable vapors. Propane, propane has to be fairly warm before it's above its flash point, right? So flash point is maybe the first thing to consider when it comes to area classification. And again, I want to make sure that we're clear on this. No one person should be classifying the area. I'm just giving you a basic understanding. So if I'm looking at a location as an inspector and I'm wondering, should this thing be classified? Maybe I can look at the safety data sheets of the chemicals involved. So we're spraying paint. I can look at the paint and I can say, okay, the flash point of this stuff is like 150 degrees F. There's no way that the paint is going to be warmer than 150 degrees F. So it's not at or above its flash point. It's the same concept when it comes to fuel dispensers, and people have a hard time with this. Gasoline, -36 to -50. When it comes to diesel fuel is like 125 degrees F. You're probably not going to see diesel fuel handled or used above its flash point very often. Really, when are you going to get a 125 degree liquid that's diesel fuel? Maybe if you have an above ground, like a metal building for storage, and you're in Phoenix or Vegas or Saudi Arabia or somewhere, but in most locations, I just can't even imagine that you're going to have to worry about diesel fuel because it's not above its flash point. The other thing that we need to consider is upper and lower flammable limits or explosive limits. Flammable limits or explosive limits are expressed in a percentage as the lowest and highest quantity of a compound mixed with air that's considered volatile. So in popular terms, a mixture below the lower flammable limit is too lean to burn or explode, and a mixture above the upper flammable limit is too rich to burn or explode. There's a Goldilocks zone, where it's not too hot and it's not too cold. It's not too soft, it's not too hard, right? So if I have a room that has gasoline vapors, if it is 99.9% air and 0.001% gasoline vapors, that's not going to ignite. There's not enough fuel. Or if I had, and I don't know how you would ever get to this point, but if you had like seriously 25% gasoline vapor and 75% environmental air, that's too rich to burn. There's not enough oxygen to sustain combustion. So that's your upper and lower flammable or explosive limits. So, defined in NFPA 30, the minimum and maximum concentrations, again the upper and lower, of a combustible material in a homogeneous mixture with a gaseous oxidizer that will propagate a flame. Clear enough? Okay, here we've got this room that has gasoline vapors. So we have a combustible gas detection system. Would I want to put that down by the floor or up by the ceiling? We know that the vapor density of gasoline is 3 to 4. So we would be putting it down here at the floor. This gas detection system is measuring percentages. What's the percentage of gasoline? What's the percentage of vapor? And is it above the lower flammable limit? Vapors from flammable liquids have a natural tendency to disperse into the atmosphere and rapidly become diluted to concentrations that are below the lower flammable limit, especially when there's natural or mechanical ventilation. And really that's kind of the name of the game. If I have flammable vapors in the room, I want to get rid of them, right? To knock out one of those three components of the fire triangle. So if I have natural or mechanical ventilation, I can remove the vapors and increase the amount of environmental air to lower than the lower flammable limit. Acetone, 2.5%. If I have 2.5% acetone and 97.5% oxygen, that will ignite. I skipped a slide here and I did that for a reason. The possibility that the gas concentration might be too rich or above the upper flammable limit really doesn't provide any safety, because in order to become too rich to burn, at some point you were in that zone that it was flammable. In other words, what if I told you that you can only have a car accident if you're going 58 miles per hour? Well, if I never exceed 55, then I would be safe, right? But what if I said, well, as long as I'm going 60, I could never have a car accident either? Well, but wait a minute. In order to get to 60, at some point you were doing 58, and you could have had an accident, right? So to say that it's too rich to burn really doesn't give you any safety, because at some point, in order to get there, you were not too rich to burn. So I only concern myself with the lower flammable limits. Acetone, 2.5. Acetylene, 2.5. Acetylene is unique, actually. Acetylene can actually burn at 100%, which is interesting. Ammonia, 1.5. Gasoline, 1.2 to 1.5. And I think the high end for the upper flammable limit for gasoline is somewhere in the area of like 7. Methyl ethyl ketone, propane, all of them have a lower flammable limit. The last characteristic that we need to know about is the auto-ignition temperature. The minimum temperature that's required to initiate or cause self-sustained combustion of a solid, liquid, or gas independently of the heating or heated element. How hot do you need to get the material before it goes kaboom? That's the auto-ignition temperature, defined in NFPA 497 and 499. So going back to our common ones, Acetone is 869 degrees F. Acetylene, 581 degrees. Ammonia, 928. Gasoline, we can all relate to that. If you get the gasoline up to 536 degrees F, it's going to go boom, right? So a cigarette cherry, when you're inhaling it and it glows, is about 1,000 degrees F. So yeah, cigarette can absolutely blow up gasoline. Methyl ethyl ketone, 759. Propane, propyl nitrate, they all have an auto ignition temperature. All right, so those are the chief characteristics that need to be considered when we're classifying a Class 1 location. So getting back to Class 1 locations, a Class 1 location, once again, is an area where flammable gases, flammable liquid-produced vapors, or combustible liquid-produced vapors might be present in ignitable mixtures. And now we know what those things are. So flammable liquids are what? Less than 100 degree F flashpoint, and combustible liquids are greater than 100 degrees Fahrenheit. So the vapors produced by them, if those are present in ignitable mixtures, then we have ourselves a Class 1 location. We break down Class 1 locations into two subcategories: a Class 1 Division 1 location and a Class 1 Division 2 location. A Class 1 Division 1 location is an area where ignitable mixtures exist, and here's the key, under normal operating conditions. What's the normal condition in this room? If I walk into this room, there is the hazard, there is an ignitable mixture. The normal condition is that in here, these barrels are open and closed all the time. We're transferring flammable liquids all over the place on a daily basis. The normal condition is an ignitable mixture. In other words, if I walk into that room smoking a cigarette, it blows up. It takes one bad thing to happen to have an incident in a Class 1 Division 1 location, because the hazard exists under normal conditions. That's a Class 1 Division 1 location. Or the ignitable mixture exists frequently because of repair or maintenance or leakage, or where breakdown of equipment would cause an explosion, an electrical ignition. So what's the normal condition in this room? The normal condition for 23 and a half hours of the day is that this is all a closed system and there is not an ignitable mixture in the room. But for a half hour of every day, I go in here and I replace these drums, and I have to open the drums while I'm doing that, so I'm releasing vapors into the atmosphere. So I have an ignitable mixture that exists frequently because of repair or maintenance or leakage, right, or the normal condition. So am I going to classify the entire room as Class 1 Division 1? Maybe. Maybe not. It's the area, right? It doesn't necessarily mean the entire room. It's what? It's an area where the ignitable mixture exists. Maybe from these drums down to the floor, I would classify as Class 1 Division 1. Again, I'm not telling you what to do. I'm just saying that that could be how the room is classified. Maybe from 18 inches up and then down to the floor, it's Class 1 Division 1. So it's an area. It's going to depend on what? The vapor density. It's going to depend on the upper and lower flammable limits, right? What percentages of vapors are required to have an ignitable mixture. Maybe this is open to the outside and there's all sorts of ventilation going through, and it's maybe not as big of a concern. So I need to look at the vapor density, how heavy it is. I need to look at the upper and lower flammable limits to figure out how much ventilation exists or needs to happen. I'm going to be looking at all sorts of different properties of the individual chemical. There's an informational note saying examples include transfer areas for flammable liquids, spray booth interiors, areas adjacent to spraying or painting operations, right? So here we're doing what? We're transferring a flammable liquid, right? Gasoline has a flash point that's less than 100 degrees F. It's negative 36 to negative 50, so that's a flammable liquid. This is a transfer area for a flammable liquid. That's a Class 1 Division 1 location. Gas stations, airplane hangars, commercial garages, anywhere where ignitable mixtures exist during normal conditions. That's a Class 1 Division 1 location. Compare that to a Class 1 Division 2 location, which is significantly less hazardous. Class 1 Division 2 location is where ignitable mixtures are stored, handled, or used, but are normally in confined systems and only escape in abnormal conditions. It's hard to see from this photograph here, but let me explain what's happening. Inside of here, they have some fuel injectors, and they're testing them, so they're spraying gasoline vapors. But this entire cabinet, can you see right here where my pointer is? That whole thing is covered in plexiglass. So it's inside of that unit. Maybe inside of the plexiglass is a Class 1 Division 1. But outside of the plexiglass, where a person might be standing, that would be a Class 1 Division 2, because the ignitable mixture inside that unit is in a confined system, and it only escapes in abnormal conditions. If the plexiglass were to break, then sure, that gasoline vapor would go into the room and that would become an ignitable mixture. But that's not a normal occurrence. That is only under what? Abnormal conditions. So Class 1 Division 2 is when the ignitable mixture exists under abnormal conditions. Or where ignitable mixtures do not exist because of mechanical ventilation that can break down. We mentioned upper and lower flammable limits. I have a room that would normally be a Class 1 Division 1 location. But I also design a ventilation system, and I exhaust some air and I bring in some fresh air to lower the likelihood of having an ignitable mixture. Well, if that ventilation equipment was to break down, then we would have an ignitable mixture, wouldn't we? So if the ignitable mixture does not exist because of mechanical ventilation, then I'm going to call it a Class 1 Division 2 location, because again, if two things go wrong in a Class 1 Division 2 location, then I can have an explosion. Somebody drives his forklift into this barrel, and somebody walks in smoking a cigarette at the same time, right? That would be a Class 1 Division 2 location. Or if the ventilation equipment stops working and somebody walks in smoking a cigarette at the same time, that's a Class 1 Division 2 location, where the ignitable mixture is normally confined, or where the ignitable mixture is prevented due to mechanical ventilation. Or we can also have areas that are adjacent to a Class 1 Division 1 location. So maybe right next to this tank, I have a Class 1 Division 1 location. Surrounding areas where the people are working might be Class 1 Division 2, and then remote from that might be an unclassified location. There's yet another informational note that says the quantity of materials, the total area involved, and the industry's safety record should be considered when classifying an area. And that's probably true not just for Class 1, but for any classified location. The quantity of the materials, going back to that nail polish salon. How much acetone do we really have here, folks? You know, we got a few bottles of nail polish remover. True. And you probably shouldn't smoke while you're removing nail polish. I agree. But am I going to classify the location? Probably not. There's not a lot of quantity involved here, and the area is large, the total area, and we have mechanical ventilation, and the industry's safety record should be considered. You ever heard of a nail salon blowing up? Me neither. So we probably ought to consider the industry's safety record. Thus far, it's shown to be a safe location. You can compare that to individual facilities that do not have a good safety record, and maybe we should classify the areas more stringently based on their safety record. So that's a Class 1 location. Class 1 locations: flammable gases, flammable liquid produced vapors, or combustible liquid produced vapors. Division 1 is where you have a hazard under normal conditions. Division 2 is where the hazard only exists under abnormal conditions, right? Somebody drives the forklift in and causes a spill, right? Some sort of an accident happened, a breakdown of ventilation equipment, things like that. So Class 1 Division 1, Class 1 Division 2. We move into Class 2 locations. Class 2 locations are hazardous due to the presence of combustible dust. All right, so what's a combustible dust? And you can see here, warning, explosion hazard, washdown of coal dust is required prior to operating the equipment. Yeah, coal dust is a combustible dust. Combustible dust is defined in Article 100. It's dust particles that are 500 microns or smaller that present a fire or explosion hazard when dispersed in the air. 500 microns. What does that mean? If you were to look at like coffee grounds in a regular paper coffee filter, that's about 500 microns. So if your combustible dust is in fact combustible and smaller than coffee grounds, then you have yourself a combustible dust. Now, we classify Class 2 Division 1 and Division 2 a little bit differently than we do Class 1 locations. A Class 2 Division 1 is where combustible dusts are suspended in the air under normal conditions. So here in the photograph, they are dumping coke dust. And that, of course, is suspended in the air. And if that's the normal condition, then that's a Class 2 Division 1 location. So it's not so much that it takes one bad thing to cause a kaboom, like a Class 1 Division 1. And, of course, a Class 1 Division 2 is what? Takes two bad things to cause a kaboom, an accident plus a spark. A Class 2 Division 1 is different. Class 2 Division 1 is combustible dust suspended in the air under normal condition. Dusts in the air are significantly more hazardous than dust accumulated on equipment. Class 2 Division 1 locations also include areas where mechanical failure could cause an explosion, or where combustible metal dust, Group E, exists in sufficient quantities. We haven't talked about group ratings, but we have Groups E, F, and G when it comes to Class 2 locations. Group E is particularly nasty. Group E is combustible metal dust, so we're talking about zirconium, aluminum, things like that. Combustible dusts are very nasty indeed. If you have combustible metal dust, you're a Class 2 Division 1, period. There is no Class 2 Division 2 location in an area that has combustible metal dust. Right off the bat, it's Class 2 Division 1. A Class 2 Division 2 location is an area where combustible dust is suspended in the air due to abnormal operations, right? So something goes wrong and then it suspends the dust. Or where accumulations of dust could exist and could be suspended due to equipment malfunction, or accumulations could slow heat dissipation of equipment. This is a photograph from a Class 2 location that was classified due to the presence of coal dust. And believe it or not, they actually clean this place very, very often. This is a pretty clean Class 2 location. But we have combustible dust accumulations, and that probably will affect the heat dissipation of this motor. So that's going to be, at a minimum, that's going to be a Class 2 Division 2 location. There's a big difference between combustible dust accumulations and combustible dust suspensions, and that's your Division 2 versus Division 1. Take a look at this video here, and we're going to see the difference between combustible dust accumulations versus combustible dust suspensions. When you think of combustible dust, you might think of things like coal dust or coke dust, some things that are actually fuel. What you might not think of immediately is more mundane dusts, like grain or powdered sugar, things, or granulated sugar for that matter. So here's a video of a young lady who made a birthday cake for her son, and she went a little heavy-handed with the powdered sugar. Now, when the powdered sugar is accumulated on the birthday cake, it's really not that big of a concern. When you suspend all the powdered sugar, that's when things get interesting. So we'll take a look here.
Happy birthday to you. Happy birthday to you. Happy birthday, dear George.
I'm not saying don't try this at home, but I'm not saying do try it at home either. That's the difference between suspended combustible dust and accumulated combustible dust. When it's suspended in the air, it is particularly nasty, and that's why it's a Division 1 location. When it's just accumulated, that's a Class 2 Division 2 location. There's yet another informational note that says the quantities of dust and the adequacy of the dust removal system should be considered when classifying an area. So I have a little wood shop in my house, and that could be a Class 2 location. And I have a dust collector in my garage. It looks nothing like this dust collector, obviously, because I don't need that dust collector, right? The quantity of the dust that I create is nothing like the quantity of dust that's created here at this facility. And the adequacy of the dust removal system. These should all be considered when classifying an area. Now, again, this is an informational note, so it's not a code rule, but it is sage advice. These are things that should be considered when you're classifying an area. Now, combustible dusts could include grain products, pulverized sugar and cocoa, dried dairy products, spices, starches, paste, potato flour, wood flour, dried hay, things like that. Those can all be combustible dusts. The last type of location that we address in the NEC is a Class 3 location. And a Class 3 location is an area that's classified due to the presence of easily ignitable fibers or flyings. And the problem with that phrase, what is an easily ignitable fiber or flying? Well, I don't know, because it's not defined. Right, seriously, yeah, it's not defined in the NEC. So if you have an easily ignitable fiber or flying, whatever that is, then it's a Class 3 location. It's not defined in the NEC. It's not defined in any NFPA standard that I've been able to locate. I've looked in NFPA's glossary of terms, and it's not there either. In NFPA 499, it defines the phrase combustible flyings. It's not easily ignitable fibers or flyings, but I think that it's probably pretty much the same concept. So combustible flyings, and this is wood shavings here that we're looking at, that is solid particles, including fibers, that are larger than 500 microns and can be suspended in air and settle down under their own weight. Okay, so in my opinion, right, because here we have this 500 micron measurement. If you have a combustible solid and it's smaller than 500 microns, we call that a combustible dust. Take the same material in a larger form, greater than 500 microns, then I think we have a easily ignitable fiber/flying. Now again, the NEC doesn't define that. It probably should. NFPA 499 talks about combustible flyings, but I feel fairly confident in saying that. So here in this wood shop, and don't read this quite yet, let's just talk about it first. There are areas in this wood shop that could very well be a Class 2 location where we have combustible dust. I would say anywhere near sanding operations is probably Class 2 because you have combustible dust, right? So if you've got a disc sander, a belt sander, something like a drum sander, that's going to probably be a Class 2 location. But if you have a table saw, you're not really creating much combustible dust. You're more creating easily ignitable fibers or flyings. Or if you have like a jointer or a planer or a wood lathe, that's probably a Class 3 location. Same material, wood fibers, but larger. So Class 3 Division 1 is an area where easily ignitable fibers, flyings, whatever those are handled, manufactured, or used, basically where they're created, right? So this might be a Class 3 Division 1 location here in this photograph. There's an informational note. These can include rayon, cotton, or other textile mills, cotton gins and mills, woodworking plants, similar facilities. We go into 500.5D2, which is Class 3 Division 2 locations, and that's an area where easily ignitable fibers or fibers or flyings are stored or handled but not manufactured. So Class 3 Division 1 is where you create the easily ignitable fibers and flyings. Class 3 Division 2 is where you store the easily ignitable fibers and flyings. Okay. 500.6, changing gears ever so slightly, we go into material groups. Equipment in a Class 1 or Class 2 location must have a group rating based on the hazardous materials. Now, right off the bat, we can see that this does not pertain to Class 3 locations. So, Class 1 or Class 2 must have a group rating. Take a look at the piece of equipment here, and it says Class 1 groups B, C, or D. Cool, so we can use it in B, C, and D, and then for Class 2, we can use it in groups E, F, or G. All right, so it's not enough to know that you're in a Class 1 location. It's not enough to know that you're in a Class 1 Division 1 or Division 2 location. You also need to know which group you're in. So what are the groups? Well, Group A is very simple. Group A is acetylene, and nothing but acetylene. The only Group A chemical compound is acetylene. Now, almost everybody that's spent much time in hazardous locations has looked at an acetylene, like an oxyacetylene welding system, has looked at it and thought, boy, is that a Class 1 location? Well, let's think about this. What are you doing with an oxyacetylene torch? You've got open flame, right? You've got an open flame. Is the room that you're in full of ignitable vapors if you have an open flame and you're hanging out and you haven't blown up? No. So the fact that you're welding in an area is evidence that you're not in a hazardous location. If you're in a hazardous location and you're welding, you blow up, you die, right? So when I say acetylene, that doesn't necessarily mean that you have acetylene. That means you have acetylene in the room in ignitable mixtures. That's Group A. Now, acetylene, when acetylene explodes, it is a more powerful explosion for a longer duration of time. When you have an acetylene explosion, it's a particularly nasty explosion. And nothing else really acts like acetylene when it blows up. So acetylene is treated as its own little animal, Group A. Now, looking back at this piece of equipment, it's suitable for groups B, C, and D. I cannot put this light in a Class 1 location that's hazardous due to the presence of acetylene. Okay, cool. That's fine. I'm not in an acetylene-enriched environment, so I'm okay. But if I was, I would need to be very careful indeed that my equipment is rated for Group A. Now, Group B is much more common. It's manufactured gas, hydrogen, butadiene, ethylene oxide, propylene oxide. There are some others. Now, why did I choose these specific ones? Because I can pronounce them. Seriously. There are other Group B chemicals. If you have the NEC handbook, there's a nice big table in there that gives you the group ratings of different compounds and the explosive limits and vapor densities and auto-ignition temperatures and everything else. Or you can get literature from Krauss-Heinz or from Appleton. They each have like a code digest that you can get, and they have all of this information for you as well. Group B is not particularly common. Group C is much more common. Diethyl ether, ethylene, hydrazine, and several others, again, most of which I can't pronounce. Group C is much more common than Group B. Normally with hazardous locations equipment, it's going to be rated for Group B, C, and D. Or it'll be rated for Groups C and D. So C and D are definitely the most common, Group D being the most common. Cyclopropane, gasoline, propane, natural gas, methane, benzene, butane, and lots of others. So Group D is your most common. When we get into Class 2 locations, we have Groups E, F, and G. Group E, which we glossed over a minute ago, that's your combustible metal dust. Aluminum, magnesium, zirconium, and similar. Combustible metal dusts are particularly nasty, and that's why you don't have Class 2 Division 2. You only have Class 2 Division 1 if you have Group E. If you're interested, take a look on YouTube and search for aluminum dust explosion. There was an incident at a place that manufactured like automobile rims, like aluminum rims, and they had aluminum dust all over the place, and they had an incident that it killed a few people, and it was really horrible. But there's a nice video on YouTube that kind of explains what happened with the aluminum dust explosion. Group F, that's your carbonaceous dust, so dusts from carbon-based materials such as coal and coke dust, carbon black, charcoal, and other carbonaceous materials. And then you have Group G for Class 2 locations, and that's everything else. Combustible dusts that are not metal and that are not carbon-based. So flour, grain, wood, plastic, chemicals, anything that's not Group E or F. Lastly, when it comes to material groups, it's worth pointing out that there are no groups in Class 3 locations. So around the table saw here, if this is deemed a Class 3 location, I don't need to concern myself with group ratings because there are no groups in a Class 3 location. So let's quickly summarize. Class 1 is what? Gases and vapors, right? Flammable gases, flammable liquid produced vapors, and combustible liquid produced vapors. The Division 1 location is where ignitable quantities exist under normal operating conditions. Division 2 is where the materials are in closed tanks and they don't escape unless we have some sort of an accident or abnormal operation. Groups A, B, C, and D are your Class 1 groups. Class 1 is governed in Article 501. Combustible dust is Class 2. Division 1, combustible dust in suspension in the air. Class 2, Division 2 is where we have combustible dust accumulations. We have groups E, F, and G in combustible dust. E is metal, F is carbon, G is everything else. Article 502 regulates Class 2 locations. Class 3 is that enigmatic, easily ignitable fibers and flyings, whatever that is, which again I said is combustible dust that's bigger than dust, over 500 microns. That's Class 3. Division 1 is where you make the easily ignitable fibers and flyings. Division 2 is where you store the easily ignitable fibers and flyings. There are no groups in Class 3, and Article 503 is the article for Class 3 locations. Let's get into 500.7, protection techniques. I'm actually going to push pause for 1 second, catch my breath, wet my whistle, and then I will be right back. So I'm sure on my video I'm going to... Okay, so 500.7, protection techniques. We know what a hazardous location is. We know how a fire occurs. 500.7 concerns itself with how to prevent that fire from happening. So protection techniques. 500.7a, explosion-proof equipment, is probably the most common protection technique, at least in Class 1 locations. So explosion-proof equipment is a protection technique for Class 1 Division 1 or Class 1 Division 2. This luminaire here is an explosion-proof luminaire. Explosion-proof equipment is defined in Article 100 as an enclosure that can withstand an internal explosion and prevents the external environment from igniting from the explosion of the surface or the surface temperature. All right, so one of the first jobs that I did as an electrician, I was wiring a gas station. And I can guarantee almost everybody that's done hazardous location work, when they first started, probably had the same thought that I did. We're wiring a gas station. We're outside doing the dispensers. And holy smokes, we're not running EMT and MC cable and stuff like I'd been doing. All of a sudden, we're running threaded rigid metal conduits and threaded couplings and unions and cap 90s, all of these weird things. And the guy that I was working with explained to me that this is explosion-proof equipment. And I thought to myself, cool. If somebody ever drives through the pumps, blows themselves up, we'll never have to rewire this gas station because it's explosion-proof. You know what I mean? And no, that's not what explosion-proof means. It doesn't mean that an explosion doesn't hurt our wiring. It means our wiring doesn't create an explosion, right? If I'm in an area that has ignitable mixtures and I have an arc, we need to make sure that that arc does not ignite the surrounding environment. And one way that we can ensure that that happens is by using explosion-proof equipment. So explosion-proof equipment, again, that's an enclosure that can withstand an internal explosion, and it prevents the external environment from igniting from the explosion or from the surface temperature. I first started this conversation by talking about that experience that we've probably all had. We are in our bedroom at night, and we turn on the light switch, and you can see a little blue arc behind the faceplate. Right? It only happens like 1 every 1,000 times, but it's cool when it does. Okay, in our bedroom, that's not a problem. In a hazardous location, that's a dead body. Right? That's an explosion. So we put our switches in an explosion-proof equipment, and that way, not if, but when an explosion happens inside that switch enclosure, when it happens, it doesn't ignite the surrounding environment. Does that make sense? So that's an explosion-proof piece of equipment. This is an explosion-proof telephone, believe it or not, right? I mean, look at this telephone. It's obviously it's unusual because it's an old-school rotary phone, but like look at the bolts and everything that this explosion-proof telephone uses. Look at this luminaire. This is not something you buy at Home Depot. You know, this is explosion-proof equipment. It can withstand an internal explosion without igniting the surrounding environments. This is another piece of explosion-proof equipment. This is just a junction box. But when it comes to junction boxes, threaded enclosures have at least 4.5 threads fully engaged, or 5 threads is the general requirement, but 4.5 is the exception, and that's found in 500.8. So threaded enclosures have at least 4.5 threads fully engaged, made up wrench tight, which cool the escaping gases to less than the auto ignition temperature of the surrounding environment. So let's say that I'm in a gasoline enriched environment. So gasoline has an auto ignition temperature, I think it was 536 degrees F is the auto ignition temperature of gasoline. I have an explosion inside of this because this enclosure is not vapor proof. Nothing is. All right, you're going to have gasoline vapors in that enclosure, and you will have explosions in that enclosure, and that's okay. The enclosure is explosion proof. What we're concerned about is we don't want the heat from that internal explosion to escape the enclosure and ignite the room, right? Ignite the building and blow up the building. So when we have an explosion inside of that enclosure, it has to swirl through these threads, right? So when we have an explosion, the threads actually expand ever so slightly, and the explosion, the hot burning gases, have to swirl through those threads. They have to fight their way out of the enclosure. And by the time that fireball leaves the enclosure, it has consumed most of its thermal energy, most of its energy, and it doesn't have enough thermal energy to ignite the surrounding environment. It's colder than the surrounding environment's auto ignition temperature. Does that make sense? It's less than, for gasoline, it's less than 536 degrees F when it escapes. So threaded fittings or threaded enclosures is one option. We also have flat joints. Those are joints that are ground to exact specifications, which once again allow the hot gases to escape only after cooling down to below the auto ignition temperature of the surrounding environment. So inside this enclosure, we have an explosion. The hot burning gases escape, but while escaping, they have to fight their way through this flange joint, and they cool off to lower than the surrounding the auto ignition temperature of the surrounding environment. It's worth pointing out also that some of these enclosures some of these enclosures have tightening sequences, just like when you change a tire on a car, right? You tighten this one, then that one, then that one, then that one, then that one. Same thing here. Some of these enclosures, you tighten this one first, and then this one, and then that one, and then that one, and they might have torque requirements as well. So you always need to follow manufacturer's instructions, but it's imperative that you follow manufacturer's instructions in hazardous locations with explosion-proof equipment or any other type of protection technique. So that's explosion-proof equipment, 500.7a. That's our first protection technique. Another protection technique is dust ignition-proof equipment. And you can see right there, dust ignition-proof. Dust ignition-proof equipment is allowed in Class 2, Division 1, or Division 2 locations. So dust ignition-proof is pretty much what it sounds like. If we go to Article 100, it's enclosed equipment that excludes dust and doesn't allow arc sparks or heat to ignite dust that's on or near the enclosure. Very similar to explosion-proof. And to be perfectly honest, let's go back. Usually, dust ignition-proof is also explosion-proof. Usually, not always. This one is just dust ignition-proof. But if I were to go back to this piece of equipment, I would bet this is probably not only explosion-proof, but probably dust ignition-proof as well. It doesn't allow dust to enter it, and it cools explosions to not ignite the surrounding environment. This doesn't allow dust to enter, and if or when we have an explosion inside of it, it doesn't ignite the surrounding dust. Same here. That's dust ignition proof. Compare that to dust tight, which is very different. Dust tight is simple. Dust tight enclosures are allowed in Class 2 Division 2 and in Class 3 Divisions 1 and 2. And by the way, I didn't say this, but dust tight is allowed in Class 3 as well. Dust ignition proof is allowed in Class 3. Dust tight is also allowed in Class 3. Dust tight is also allowed in Class 2 Division 2. Now this is a dust tight enclosure, but that's a very extravagant version of dust tight. This is also dust tight, a regular outdoor box with a gasket. All that dust tight means is it's an enclosure that doesn't allow dust to enter it under specified test conditions. If you have an outdoor box and you got a gasket, is that dust tight? Yeah. Is that dust ignition proof? No, not by any means. But it might not need to be, right? If I'm in a Class 3 Division 2 location, Class 2 Division 2 location, I only need dust tight, not necessarily dust ignition proof. So dust tight is actually pretty simple. Purging and pressurizing is another protection technique. Purging and pressurizing is allowed in any location that it's identified for. So Class 1, Class 2, or Class 3, whatever it's designed for. Identified is a term that doesn't necessarily mean marked. Identified just means that it's recognizable as being suitable for the application. So in other words, it's designed for that installation. So purging and pressurizing is allowed in any location that it's manufactured for, that it's designed for. Purging and pressurizing, again, is defined in Article 100, and that's supplying an enclosure with a protective gas to reduce the flammable gases or vapors, and that's the purging part of it. So it's a two-part approach. Number one, you purge the equipment. You supply gas, and you get rid of all of the flammable gases that are inside the equipment, right? You purge it. So you might use nitrogen. That's a very common method. You pump a bunch of nitrogen into an enclosure. Nitrogen is inert. It's a protective gas. Or you could use clean air, outside air, and you purge all of the bad stuff out of the enclosure. That's the purging. And then step two is the pressurizing. You pressurize it. You keep it pressurized to prohibit the entrance of gases or vapors. So let's go back here. Step one, I purge all the bad stuff out of the equipment. Step two, I keep it pressurized so that the bad stuff can't enter the equipment, right? So that's purging and pressurizing. Purging and pressurizing comes in three different flavors: type X, type Y, and type Z. And off the top of my head, type X allows you to go from a Division 1 to a Division 2. And type Y is from Division 2 to unclassified, and type Z is from Division 1 to unclassified. Now, don't quote me on that, but off the top of my head, those are the three different types of purging and pressurizing. We have intrinsic safety. Intrinsically safe equipment is allowed in any classified location, and only Article 504 applies. So intrinsically safe equipment is basically a circuit that cannot ignite the surrounding environment. There's not enough voltage and current to create enough energy to ignite the surrounding atmosphere. You take these conductors from the intrinsically safe system and bang them together, and you cannot create an arc, right? Not enough arc to ignite the surrounding environment. So an intrinsically safe system is allowed anywhere because you can't blow anything up. It's not a source of ignition. So again, that fire triangle. If I can't remove the oxygen and I can't remove the fuel, I could just remove the ignition source, and that's intrinsically safe, right? So that's intrinsic safe. Non-incentive circuits, non-incentive equipment is similar to intrinsic safety, but non-incentive equipment components and circuits are only allowed in Class 1 Division 2 or Class 2 Division 2 and Class 3 locations. Okay, an intrinsically safe system, you cannot create an ignition with it at all. No matter what you do with it, you can't create an ignition. With a non-incentive circuit, you can't create ignition under normal conditions, but you can create ignition under short circuit conditions. And because of that, it's only allowed in Class 1 Division 2 locations, right? Not Class 2 Division 1. Non-incentive, defined again in Article 100, that's equipment that has circuitry that's not capable under test conditions of igniting a specified volatile mixture. So that would be a non-incentive equipment. Very low voltage, very low current, pretty much just for a signal. Hermetically sealed is another protection technique. That's hermetically sealed is allowed in Class 1 Division 2, Class 2 Division 2, or any Class 3 locations. Hermetically sealed is defined also in Article 100. That's equipment that's sealed against an external atmosphere. It might be a little bit hard to see, but can you see here where it says Leeds factory sealed? Perfect. This chamber is hermetically sealed. All right, so that is a hermetically sealed enclosure. The last protection, actually not quite the last protection technique, item K, combustible gas detection, are only allowed in industrial establishments with restricted access and qualified persons maintaining the equipment. So there's a lot of criteria in order to use a combustible gas detection system, but they're quite good. They show the lower flammable limit or lower explosive limit, and they will set off an alarm letting you know that the lower limit has been exceeded. This is a combustible gas detection system that is detecting a lighter than air gas, right? Hence the detection is up at the ceiling level. And then the indication equipment is here. So a protection technique that uses stationary gas detectors in an industrial establishment. The last protection technique is subsection L, other protection techniques. Other protection techniques that are identified for hazardous locations are allowed as well. The code doesn't tell us what these might be, but an example might be zone-rated equipment that is specifically identified for use in a class division location. So zone-rated equipment under certain conditions could be used, like flame-proof equipment. So looking at this piece of equipment, you can see that the marking is very different than what we would see here in the US under a normal NEC regulated installation. This is ATEX rated equipment, and I mentioned earlier, you can only use zone-rated equipment if it bears the mark AEX. And even then, you're limited on how you can use it. So that's item L, other protection techniques. Just about done. 500.8 equipment. A, suitability. Equipment must be judged suitable by number 1, listing, or number 2, evaluation from a qualified testing lab or product inspection agency, or 3, other evidence. So I was an inspector for 17 years. I don't require everything in the world to be listed because the code doesn't require everything to be listed. But when it comes to hazardous locations, I need to determine suitability. And I'm looking for listed equipment. So here in the photograph here, this is from UL's online certification directory. I'm going to look at my particular luminaire, and I'm going to ask, okay, is this thing listed? I can look it up on their website, and this one from Cooper Krause Hines is a listed piece of equipment. Now, I say this all the time. Nothing in the world has to be UL listed. UL is one testing laboratory. There are several others. Intertech is another testing laboratory. Met Labs is another. There are all sorts of testing laboratories. So I'm showing the UL online certification directory, but that doesn't mean that anything has to be UL listed. Intertech, I was teaching at their facility in New York a couple of weeks ago. They have a fantastic facility, and they test and list and certify all sorts of hazardous locations equipment. In fact, I was doing this lecture, this hazardous locations lecture, with Intertech, and yeah, Intertech listed equipment is great. There's nothing wrong with that. So you can look at listing, or you can use evaluation from a qualified testing lab or product inspection agency. Maybe my product isn't listed, so instead of the manufacturer sending the product to UL or Intertech, maybe instead we have Intertech come to our facility and do a field evaluation on the product. And they'll look at it and determine in the field whether or not it can be used, whether or not it's suitable. So, may not necessarily have to be listed. Perhaps field evaluation is okay, and that's item 2. Or item 3, other evidence. Manufacturer's self-declaration, things like that. B1, approval for class and properties. Equipment has to be identified for the location and the specific gas or dust, etc. And the equipment must not operate above the auto-ignition temperature of that material. Alright, so here we have a piece of equipment. It's a luminaire. It's listed for use in Class 1 Division 1, but only in groups C or D. Again, it's not enough to know that I'm in a Class 1 Division 1 location. I need to know the group. And in order to know the group, I need to know the specific chemical compound that drove the hazardous location classification. So, can I use this in an area that's hazardous due to the presence of acetylene? No, because acetylene is group A. So I can't use this in a group A environment. Class 1 Division 2, groups A, B, C, and D. Class 2 Division 2, groups F and G. So there you go. It has to be identified for the specific gas, dust, etc., and it must not operate above the auto-ignition temperature of that material. We're going to talk about what we call T codes here in just 1 second, but that's having to do with the auto-ignition temperature of the material. What is making my location a hazardous one? Is it acetylene? Is it butadiene? Is it gasoline? Is it propyl nitrate? I need to know these things because I need to know what? The auto-ignition temperature of the material. Luminaires have a lot of surface heat. I better make sure that it doesn't have so much heat that it blows up the building, right? So I need to know what the auto-ignition temperature of the material is. Equipment that's suitable for a Division 1 location can also be used in a Division 2 location if it's rated for the same group, temperature, etc. That makes sense, right? A Class 1 Division 1 is much more hazardous than a Class 1 Division 2. So if it's rated for a Division 1, then I can use it in a Division 2. Now, we have to be careful here. Equipment rated for Class 2 can't be used in Class 1. I know some people look at it and they say, "Well, man, explosion-proof equipment, that's the creme de la creme, and there's nothing worse than a flammable gas explosion." No, a combustible dust explosion can level a building easily. So it's not that a flammable gas is more hazardous, it's just a different hazard, right? So we need to protect against the specific hazard. So again, equipment that's suitable for Division 1 can also be used in Division 2. So this piece of equipment says Class 1 Division 1, Group A, B, C, and D. And the little star here says that Group A is UL only, as opposed to CSA. So in other words, in Canada, Canadian Standards Association, I can't use this in Group A. But in America, UL, I can use this in Group A. So Class 1 Division 1, Group A, B, C, and D. Can I also use it in Class 1 Division 2? Yeah, of course. This says Class 2, Group E, F, and G. Well, is that Division 1 or Division 2? If it just says the class, then it's both. I can use it in Class 2, Divisions 1 and Divisions 2. Class 3, Division 1 and Division 2. Item B3 is something that really throws a lot of people. General purpose equipment, discussed in Articles 501 through 503, is allowed in Division 2 locations if the equipment does not create an ignition source under normal conditions. Alright, so here we have this general purpose 4 square box or 1900 box, depending on where you are. This is okay in a Class 1 Division 2 location. We're not expecting explosions in Class 1 Division 2 locations. It requires two bad things, right? Some sort of an incident and a source of ignition. So think about it. How would this splice box, now there's no arcing sparking devices, it's just a splice. How would this create an ignition source? It would have to require, like, somebody drives the forklift into the barrel of acetone, and at the same time, an electrician is in this box working energized, which they should never be doing, working energized and blowing themselves up while the guy drives the forklift, right? In Division 2, we're not expecting explosions. So you can use general purpose explosions if it does not create an ignition source under normal conditions. If that's a switch, no, it can't be a general purpose enclosure because that is an ignition source, right? Make and break contact. But if it doesn't create an ignition source, general purpose enclosure is okay. B6. Equipment must be identified for all gases or dust that will be present, including multiple gases or dust. So here we have an explosion-proof telephone. Class 1, Groups B, C, and D. Can't use it in Group A, right? Class 2, Groups E, F, and G. Perfect. The last thing here, well, not the last thing, pardon me, but 500.C, the next thing, marking. Equipment markings must include the class 1, 2, or 3, the division, divisions 1 or 2, and the group rating, A, B, C, D, E, F, or G. So Class 1, Division 1, and Division 2, Groups B, C, and D. So again, boy, if you're in an area that's hazardous due to acetylene, not a lot of options for you. Class 3, Divisions 1 and 2, there you go. This is something that I've found a lot of people in the industry don't know about, and that's temperatures, T-code ratings. Luminaires, motors, and other heat-producing equipment must be marked with a temperature range, or a T-code. Okay, here we have a luminaire, and in an ambient temperature of 40 degrees C, now 40 degrees C happens to be one of the few Celsius measurements that I know. 40 degrees C is 104 F. So let's just say room temperature. If you're installing this light in room temperature or colder, 104 degrees or colder, which is room temperature, then this luminaire is rated T3 as it relates to a T-code. T3, that's the globe. T3 if I have an 8-inch refractor, but if I have a 12-inch refractor on this luminaire, it's actually a T-code T3A. Okay, so what does that mean? Fine, it has a T-code, great. Well, what do I do with that information? Well, if I go to table 500.8c, I can look at what the T-code means. So this is a type T3, and I go to 500.8c, my T-code, T3, means that this luminaire can operate at temperatures up to 392 degrees F. And of course this is also a T3A if I have a 12-inch refractor, which means with a 12-inch refractor it can reach temperatures of 356 degrees F. Okay, so that's my maximum temperature. Why do I need to know that? Well, if my auto ignition temperature of the chemical that made my hazardous location a hazardous one, if my chemical ignites at 392 degrees, well then I better not put this light in that environment, right? Now, a T3 luminaire is a pretty cool running luminaire, Acetone requires 869 degrees F to blow it up. Ammonia is 900 plus. NEC 750, gasoline 530. But what if I'm doing a building that's hazardous due to the presence of propyl nitrate? Very low auto ignition temperature, only 347 degrees F. Well, that T3 luminaire can hit temperatures of 392 degrees F. I had better not be using that light in an environment that's classified due to the presence of propyl nitrate. So, it's not enough to know that you're in a class 1. It's not enough to know that you're in a division 1 or a division 2. It's not even enough to know that you're in a group A, B, C, or D. You need to know the specific chemical and the specific properties of that chemical. The vapor density, the upper and lower flammable limits, the auto ignition temperature, the flashpoint. All of these things have to be known when classifying a location, and indeed when wiring a classified location. And that's why the documentation required in 500.4a is so important. You have to have all of this information. Same thing, by the way, is true for class 2 locations. Some of the more common ones, iron is 290 degrees F, magnesium 430 degrees. Same concept with temperature codes. So luminaires, motors, heat producing equipment. It's not quite as big of an issue as it once was as it relates to luminaires, because now we're using LEDs, right? But boy, you take a metal halide or a mercury vapor, and yeah, those lights can get pretty hot, obviously. 500.8e talks about threading. Conduit threads can be either NPT or metric, and they must be made up wrench tight to avoid arcing during a fault and to allow the escaping gases to cool. So again, we have an explosion inside of the conduit system. We need to make sure that those hot burning gases have to swirl through the conduit threads, fight their way out, and cool themselves off to a temperature that's lower than the auto ignition temperature of the surrounding environment. Equipment for NPT threaded conduit and fittings must engage 5 threads, but there's an exception. Listed equipment only needs 4.5. So I need to spin this thing in there, make it up wrench tight, and make sure for listed equipment that it gets at least 4.5 threads. For non-listed equipment, at least 5 threads. Unused openings have to be closed with listed plugs, having at least 4.5 threads fully engaged. So we've got to make sure that we've got a listed close-up plug for that unused opening. Optical fiber cables, with or without electrical conductors, have to be sealed in accordance with Articles 501, 502, or 503. We're not going to cover that tonight because we're not going to get into Articles 501, 502, or 503. But suffice it to say, optical fiber cables are not electrical. So why do I need to concern myself with that? Well, you can still transmit gases through openings around an optical fiber cable. So if we were getting into the sealing rules, it would make sense, but I'm not going to cover all of Chapter 5, at least not for free. The last thing is 500.9, specific occupancies. And here we just have a reminder that Articles 510 through 517 cover specific hazardous locations that are commonly encountered, like gas stations, commercial garages, things like that. Earlier I said Articles 510 through 516, and really I stand by that. Article 517 is healthcare facilities, and healthcare facilities can have flammable anesthetics, but we haven't used flammable anesthetics in the developed world for probably 50 years. You're not going to find flammable anesthetics in a healthcare facility, so you're not going to have a hazardous location in a healthcare facility. Not like you would. Well, you're not going to have flammable anesthetics. I shouldn't say that you're not going to have a hazardous location, but you're not going to have flammable anesthetics like perhaps you would have back in the 1950s. With that said, we made it through Article 500. I'd like to thank you guys for joining us. It was nearly a 2-hour discussion. Hopefully you got something out of this. If you did, please leave a comment. And as I mentioned earlier, if you have any questions, please don't hesitate to reach out and get in touch with me. It's my pleasure to help you guys out. So with that said, thank you once again, and have a great day, everybody. Be safe out there.